Hello. This will be a demonstration of proposition 13 from book 9 of Euclid's Elements, which says that if numbers be in continued proportion beginning from the unit and the number after the unit is a prime number, then the greatest number, that is the last number, will only be measured by those numbers which preceded in the continued proportion. We're given four numbers A, B, C, and D, which are in a continued proportion beginning from the unit, so that the unit is to A, just as A is to B, just as B is to C, and just as C is to D. We're also given that the number A, the number next to the unit, is a prime number, so A is prime. And what we want to prove is that the number D, which is the last and the greatest in the continued proportion, is measured only by A, B, and C, which preceded in that continued proportion. So there's going to be no number other than A, B, and C, which measure the number D. For if this is not the case, then there will be some number E, which is not the same or is not equal to A, B, or C, and it measures D. So the number E is not equal to A, B, or C, and the number E also measures D. Now, if the number E is a prime number, then what's going to happen is that the number E will measure the number A. We know this from the previous proposition 9.12. Because the number E measures the number D, we made the number E in that way. And we know from proposition 9.12 that any prime number which measures the last number in a continued proportion, which begins from the unit, will also measure the second number from the unit, so that because the prime number E measures the prime number D, the prime number E will also measure the prime number A. But you'll remember that the number A is prime itself. We were given that, and we know from the definition of prime numbers, that is definition 7.11, that prime numbers are only measured by the unit and themselves. So the number E, obviously not being the unit, must therefore be equal to the number A because it measures the number A. But we know that the number E is not equal to the number A. We made it in that way. And so what happens if E is a prime number is that it is both equal to and not equal to the number A, which is impossible. And so we can conclude that the number E is in fact not prime and is therefore composite. And we know from proposition 731 that every composite number is measured by a prime number. Next, we're going to prove that the number E is only measured by the prime number A. For if this is not the case, then there will be some prime number K, which is not equal to the number A, and which measures the number E. So K is a prime number. It's not the same with A. It's not equal to A. And the number K also measures the number E. Now, a similar thing is going to happen. We know that the number K measures the number E. We made it in that way. And we know that the number E measures the number D. We made it in that way in our first step, which therefore means by a property of numbers that the number K also measures the number D. And again, by proposition 9.12, because the number K measures the last number in a continued proportion, which begins from the unit, proposition 9.12 tells us that the number K will also measure the second number from the unit, which is the number A. But again, we know that the number A is a prime number, and we know prime numbers are only measured by the unit and themselves, so the number K, obviously not being the unit, is therefore equal to the number A, for it measures the prime number A. But we made the number K to be not equal to the number A, to be unequal with the number A. And so what happens is, if there is a prime number other than A, which measures E, then this prime number will both be equal to A and not equal to A, which is impossible. And so we can conclude that the prime number A is the only prime number which measures the number E. Next thing we're going to do is we're going to create the number F, and F will be the number according to which E measures D. That is to say, E times F, the product of the numbers E and F, is the number D. Now next we want to prove that the number F is not the same with the numbers A, B, and C. For if it is the same with the numbers A, B, and C, then A, B, and C will measure D according to E. How do we know this? Well, we know that the number F measures the number D according to the number E. This simply follows from the fact that the product of E and F makes the number D, so we can say by the definition of multiplication, definition 7.15, that the number F measures the number D according to the number E. But if the number F is equal to one of the numbers A, B, and C, then A, B, and C will measure the number D also according to the number E. But we know that the number A measures the number D according to C, the number B measures the number D according to the number B, and the number C measures the number D according to the number A. We know this from the porism of proposition 9.11. So what you'll notice, just going through that very briefly again, if we want to know how many times the number A measures the number D, what we're going to do, we're going to count how many steps the number A is away from the unit. It's just one hop away. So we do one hop backwards beginning from D, we land on the number C. And so we say that the number A measures the number D according to the number C. And in a similar way, we would show that the number B measures the number D according to itself, the number B, and that the number C measures the number D according to the number A. But we also know that the numbers A, B, and C, or one of them, measures D according to the number E. We had shown that in the previous step. And so what follows from this is that the number E has to be equal to one of the numbers C, B, and A, because A, B, and C measure D according to C, B, and A, and if they also measure D according to E, then E has to be equal to C, B, or A. But we know that the number E is equal to none of those three because we made it in that way in our first step. And so what happens if the number F is equal to A, B, or C is that the number E is both equal to and unequal with the numbers A, B, and C, which is obviously impossible. And so we can conclude that the number F is not equal to the numbers A, B, and C. Next, we want to prove that the number F is a composite number and that it is also measured by the prime number A alone. We would do this in a similar way to how we prove that the number E is a composite number and that it's measured by the number A alone. So that would be steps 2 through 3 to prove that the number F is composite, and steps 4 through 6 to prove that the number F is measured by the number A alone. Now, we know that the product of E and F is the number D. We made the number F in that way in our 7th step. But we also know that the number A times the number C makes the number D. How do we know this? Well, we know this also from the porism of proposition 9.11. That one will help us say, or will tell us, rather, that the number A measures the number D according to the number C, which is equivalent to saying that the number A times the number C makes the number D. But what we have here is we have two products which are equal to the same number, or they make the same number. So common notion 1 tells us that they are equal to each other, so that the product of A and C is equal to the product of E and F. But we know when two products are equal to each other, the extreme, or the four numbers that make up the two products are proportional. That's what proposition 7.19 tells us. So that because A times C is equal to E times F, we can say that A is to E just as F is to C. But we know that the number A measures the number E. We have proved that in our 6th step. So by the definition of proportionality, which is definition 7.20, we can conclude that the number F also measures the number C. The next thing we're going to do, we're going to create the number G, and G will be such that F times G makes the number C, or in other words, that F measures C according to the number G. Now, in a similar way to how we prove that the number F is not equal to the numbers A, B, and C, we can prove that the number G is not equal to the numbers A or B. That would just be going through similar logic to steps 8 through 10. And we can also prove that the number G is measured by the number A alone in a similar way to how we prove that F and E are measured by A alone. And similarly also, according to steps 12 through 13, we can show that the number G measures the number B because it'll be equal to how the number A measures the number F. And A will be to F just as G is to B. We can rehash that logic if we want to. I'm not going to because it's the exact same. But the point is that the number G measures the number B. Now the final thing we're going to do, we're going to create the number H such that the product of G and H is the number D is the number B. My bad. G times H makes the number B, or in other words, that G measures B according to H. And in a similar way to how we prove that f is not equal to a, b, and c, and how we prove that g is not equal to a or b, we can prove similarly that the number h is not equal to the number a. And similarly also to how we prove that the number f measures the number c and that the number g measures the number b, we can prove that the number h measures the number a. But we know that the number a is a prime number. We were given that, and we know that prime numbers are only measured by the unit and themselves. That's definition 711. So that the number a, obviously not being the unit, must then be equal to the number a, for it measures the number a. But you realize what we have here is that the number h is both equal to and unequal with the number a, which is an impossible state of affairs. And so what we can conclude from this whole thing, all these reductios, is that there is no number other than a, b, and c which measure the number d. That a, b, and c are the only numbers which measure the number d, which is precisely what we set out to prove, which means we're done with the proposition, therefore, etc., q, e, d. I hope that wasn't too hard to follow. This proposition is a mess. It's not a mess, actually. It's very focused. It's just very brutish. It's a lot of the same thing over and over again. There's tons of reductios. As far as I know, this is the most reductios in any one proposition of Euclid, which is nice because I don't want to do another proposition like this. This was not very fun to write out. I don't have too much to say about this proposition. I will give an example of what this looks like. So say we have a continued proportion which begins from the unit. So let's just do the powers of 2 again. So 1, 2, 4, 8, and we'll stop at 16. We know the number 2 is a prime number. So what this proposition 9.13 tells us is that the number 16 is only measured by 2, 4, and 8. There will be no number other than 2, 4, and 8 which measure the number 16. And that's easy enough to verify. 3 doesn't measure 16. 5 doesn't measure 16. 6 doesn't. 7 doesn't. 9 doesn't. You can go all the way up to 16 and show that there is no number other than 2, 4, and 8 which measure the number 16. Now you might think that this is kind of a trivial result if you know what's called the fundamental theorem of arithmetic. I won't go into too much detail about it here, and I certainly won't prove it in this video. But the point is what you'll realize, we know this from proposition 9.8, right? That continued proportions, which begin from the unit, are just the different powers of the number second from the unit. So you know that 2 is just 2 to the power of 1, 4 is 2 squared, 8 is 2 cubed, and 16 is 2 to the 4th. You can continue that forever. And if you know this, then it seems fairly obvious that the number 16 is only measured by 2, 4, and 8, because its prime factorization, we would say, is just a bunch of 2's. Briefly to explain what exactly I mean by the fundamental theorem of arithmetic and what I mean by prime factorization is that what that theorem says is that every composite number can be represented as a unique product of prime numbers. So for example, 6 is 2 times 3, and it's the only number that you get from 2 times 3. 10 is 2 times 5. Those are prime numbers, and their product is 10, and 10 is the only number which is the product of 2 and 5. 2 times 7 make 14. Those are both prime numbers. 3 times 7 makes 21. You can keep going like that and show that for every composite number, it is equal to the product, a unique product of prime numbers. So why this proposition might seem kind of obvious if you know this is that, well, the prime factorization of 16, the prime numbers which make up the number 16 are just 4 2's. It's just 2 times 2 times 2 times 2. So it's fairly obvious that 3 isn't going to measure 16, that there's no prime number which measures 16 other than 2, and its various powers leading up to it. Now, this sort of proposition will help us to prove the fundamental theorem of arithmetic, which is why this is not a trivial result. This goes back to something I was talking about in my video on proposition 9.3, where it would seem if you knew exponent rules that that proposition was kind of trivial, but you would realize that the logic laid out in proposition 9.3 helps you get to those certain exponent rules. It's similar to this. This is going to help us get to that fundamental theorem of arithmetic, that all composite numbers are a unique product of prime numbers. Now, will I ever get to proving that in a video? Who knows? Maybe not. I'm not sure. I'm not married one way or the other. It would be cool though, because I mean, it's the fundamental theorem of arithmetic. It's very, very important. It's like the Pythagorean theorem or other fundamental theorems like fundamental theorem of algebra or calculus. So it would be important to demonstrate it. So I might do that at some point, but this is kind of closest we'll get to the fundamental theorem of arithmetic, at least in Euclid, because Euclid doesn't prove it, which is kind of interesting. But this is the closest we'll get. So I hope you're happy with this proposition. It's not my favorite. I can't imagine it's anyone's favorite, but you got to go through it if you want to go through all the elements, so that's why I've demonstrated it. That being said, I'm going to end the video here and move on to proposition 9.14.